Hello, everybody. Welcome to Test 4 Review Day. Here we go. We've had a lot of good requests. I'm going to take it from Spring 18, Test 3, starting with Part 2 reactions. And after analyzing this reaction, I realized there's going to be almost equal amounts of two major products, so I cut that first box in half. Let's do the analysis to see what I was talking about. My computer's doing some squirrely things already. Cross your fingers, everybody. Rx is what we analyze first always. That's the carbon with the leaving group. I need two things from you right now. I need the category of the Rx. Sorry about that. Category is secondary. The carbon with the bromine has two bonds to carbon. And your conclusion based on that is that you do not know if it's SN1 or SN2. So you show me that by doing at least this. This is about a bare minimum to get full credit for that first part. You could make it a full sentence. The Rx is secondary, which leads us to believe it could be S1 or SN2, but who has time for full sentences, right? 2, the nucleophile. Please, in this order, do not change the order. Our flow of our thoughts should always be Rx first, nucleophile second, solvents third. Nucleophile is alcohol. Poor solvent. Poor nucleophile. I was thinking ahead to solvents, wasn't I? And that's not even a category. Poor leads us to think about SN1. Solvent. ROH as well. When the solvent appears to be missing, then the nucleophile and solvent are the same thing. Polar, it's very polar when it has O bonded to H, but more importantly, it's protic with O bonded to H. Both of those lead us to talk about SN1. Your conclusion, I'm not going to get fancy with the two colors anymore. I got one thing saying I don't know, and the other two things saying SN1. I'm going SN1. Carbocations. Just threw that out there. Every time you think about SN1, you think about carbocations. And when you think about a secondary carbocation, you always look at it and ask yourself, if there's a carbocation here, can it rearrange by moving either hydrogens or carbons to get to a more stable cation? And the answer is yes. I could rearrange by taking the H from the right and putting a carbocation there. When I move the H over, then this will be the carbocation. So one of the major products will come from that. The H moving. I'll do my best here. H moved there, so it's now a CH2. The nucleophile, my colors. I know I said I wasn't going to go with colors, but I do like to keep some things consistent. Stereo center here, I didn't do anything yet. CH became CH2. And my nucleophile is the oxygen. Please don't pretend the methyl is the nucleophile. The methyl doesn't have a pair of electrons to make a bond. Yet every semester I see students list it because that's the direction it's typed. CH3, CH2OH, and they type it right there, CH3, CH2OH. They have an octet violation right away, and they don't know that the lone pair is what makes it a nucleophile. And it just makes me sad every time. Please, go to stick figures anyway. O, CH2, CH3. In the intermediate stage, there's an H on the O, which makes an oxonium. Please do not put an oxonium in any box on this question anytime. Those are strong acids. They will be neutralized by the solvent. So that's one. And if I have the cation here, this is branched as well. If there's a branched carbon, one away from the carbocation, then rearrangement should be in your mind. So I'm going to rearrange this H to here and have a cation there, and it won't be it'll be becoming a stereocenter again, but it'll be racemic. Dangerous word, don't use it. Methyl there. C, moved an H, and your O ethyl's right there. O ethyl. And a minor product would be the SN1 product. And oh, here's a stereocenter that you have to tell me you know what happens to. What happens to stereocenters during SN1s with carbocations? You say 50, 50, RS. Same for this product here, where you do a non-rearranged SN1. You won't get as much because it's from a secondary carbocation. Not as stable. And it has an isopropyl here and an O ethyl here. Same comment. You don't even have to rewrite it. Nope, it's not there. It's there. My O ethyl looks like a strange sigma or something. I don't even know what it looks like. O bonded to a CH2, CH3. Okay. And I don't want people saying, is that CH3 attached to that C up there? No. Minor. Uh-oh, we're out of options. What do we do? What do we do? Oh, that's right. For every SN1 reaction, the minor is E1. So just take a look at the cations that we talked about. Don't put them in the boxes. Cations will not get you points on this question. 3 cations to choose from, so you could make many minor products in this question. One of the cations was here. One of the cations was here. And you could have a third cation right here. Right there. I think I gained a carbon on that one. No, it's not where the cation is. That's why. Stereocenter still there. Yeah. Cation was there. So you can make double bonds here. Remember, that carbon has to be part of the double bond. Double bond there would give this minor product. Or to the other side. I'll put it in the same box. I'll just show you there's more products here than we have boxes for, which is probably on your test too. And no, that does have an extra C. That one's Z, and you could also draw the E version of the same alkene. And we're going to do one from over here where we could make this into this one by grabbing that H, or down here, which would be a unique alkene that we haven't drawn yet. That's all the possible ones. Those are all E1. These are all SN1. SN1. And that's that. Probably going to have you draw a leaving group that's not one of the traditional halogen leaving groups. If you don't know, that's a nitrate, the conjugate base of nitric acid. And yeah, you should know the conjugate base of perchloric acid, toluene sulfonic acid, nitric acid. And is that all of them? that are not halogens? Maybe. I'm just talking. So as I'm talking and I'm writing, often bad things happen. Nitrate ions got a interesting Lewis structure. Lots of charges, yet it's fairly stable. You have a stray dot there, but I'm not going to bother. I'm not going to try. No stray dot right there. It's Lewis. Stray dots are not good. We haven't even done our analysis. RX. Secondary. Same story. Nucleophile. RS minus. Strong. So that's its category. Conclusion. SN2. Solvent. I'll draw the solvent out because maybe this will give you a clue. Some of you thought it was an ether by mistake. Can't be. You'd have an octet violation or a formal charge. Either one's not this thing. It's acetone. Polar aprotic. Also SN2. Okay. You get two things saying SN2 and one saying I don't know. So it's kind of like the first one, except we have a different conclusion. So you're not making carbocations. Therefore, you're not rearranging carbocations because you can't rearrange something you didn't make. Therefore, give me just the SN2 product. Backside attack. And we got our green carbons here. No rearranging going on when there's no carbocations. Backside attack. That pushes the H to the back. And the nucleophile comes from the front because the leaving group was in behind before. SCH3. You could draw that, or S with a stick. There you go. 2 points because there's a stereo center involved. So far, so good. And we're moving on. We had a request for this whole section, so it's pretty good. It helps review all of chapter 9. Seriously, this thing does review all of chapter 9. Major and 4 minors, and you're thinking, oh, it's that SN1 one with the E1s is minor, and you might be wrong about that. ETNHK. Remember what you do with K all along in this course? That's the conjugate base of an amine. That is a pKb of 14 minus 40. That is an incredibly strong base, and definitely that's a hot set of conditions. Strong base plus heat, E2. We'll write it down somewhere over here. Don't ever skip 1, 2, 3. You're just throwing points away if you skip 1, 2, 3. RX tertiary. So you're thinking SN1. I have a fingernail on the chalkboard situation with my new screen. Okay, I just had a shiver on my spine. Nucleophile, RNH minus, strong. SN2. But this is one of those override factors. Also, a strong base plus heat. That's an override that creates E2 as the only thing that happens. 3, so I shouldn't have put that in red, but that's okay. I'll switch my solvent to black here. RNH2. If it has OH or NH, it's polar protic. If it's polar protic, our conclusion's SN1, but we overrode that with our strong base and heat. So I want to see E2 products, major and minor. Remember, a phenyl A phenyl has double bonds in it. You don't need to draw the phenyl for me. This is not a nomenclature question. But I do want to remind you that if you can make a double bond there, it can resonate with the phenyl, and that is the best kind of stability you've got. And yeah, that's a beta position there. Look. Oh, as soon as I knew it was E2, I better be thinking alpha, beta, 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 and the best beta creates a double bond that can resonate with the phenyl. That's my major right there. You can draw phenyl, it's fine. Double bond there, methyl here. And you can say, right, that'd be major, and this same position, but now the propyl's over here. Methyl's there. Those are two different molecules. One Z, the first one is E. And sterics say that that'll be major, and this is Z. And we can do minors. We can do a minor to this beta here. And we don't even have to say which ones are more minor or less minor, or whatever one minor you want to say. So let's just go around here. Double bond there. Phenyl. Double bond has to be between alpha and beta, or else you don't know what you're talking about. This mechanism does beta H removal and alpha leaving group leaves. That's the whole story right there. And that will not be a wedge or a dash anymore. It's now sp2. It's flat. And there's no EZ isomer for this one. But the last one, where you make a double bond here, has EZ isomers again. So methyl here, double bond, and then you're going to have an ethyl left over down here after you take the H. So there, and switch ethyl over to the other side and H on the other side. Those are different molecules. We got the E version here and the Z version there. You don't even have to tell me they're E or Z. I don't care. But over here, when I had to give a major, I got the bulky group here. And which of these two is bulkier? Propyl's bulkier than a methyl. I want them anti to each other for major and syn to each other for minor. Good story. And this next one is my favorite. It's an NGP. Do you want to know how I know? You got to wait for it. You don't have to wait very long. Rx is tertiary. You're thinking SN1, but Rx has RSR new. NGP, neighboring group participation. Want me to say that slower? Neighboring group participation. Nucleophile R3P. This is the other nucleophile, the one that's not in the same molecule, is moderate. How do I know that? Because it's not on my list of moderate nucleophiles. Very sad. But we have R3N on the list. Tertiary amines are moderate. When they're moderate, we don't know if they're SN1 or 2. And the solvent is hexane. Definitely non-polar. Category non-polar, conclusion SN2, because non-polar destabilizes carbocations. There you go. This is the only one I'm going to do the mechanism here because I can't do the products without doing the mechanism myself. The neighboring group part is first. It changes the whole ball game. And you make this, it's not going to be a triangle. It's going to be a square, isn't it? Count the atoms from sulfur to this carbon around. 1, 2, 3, 4, square. And it comes in from the back side of this dash, so the sulfur will be on a wedge bond. So your intermediate, don't put this in the box, it's not your final product. It's an intermediate. The sulfur will be on a wedge, and the sulfur comes up to a CH2, to a C, to this C. And none of the other bonds around the ring were changed. There's a methyl here. CH2, CH2, dimethyl. Don't need wedge dash there. Now the question is, to get the square to pop open, you've got to attack one of the carbons attached to the sulfur. And interestingly, you know, I didn't see this till now, but the carbon on top has 3 carbons attached. The carbon down here has 3 carbons attached. It's a tough call. Which one's less hindered is the question when you do the NGP. Well, I'd have to say the one that has 2 methyls is a little less hindered than one that has this CH2, and this CH2. Although this is the same CH2 attached to this carbon as this, so you can call that a tie. So I'm comparing the second methyl to the CH2 here. Let's just say it's less hindered here, because it is. You're going to pop it open down there, nucleophile. Going to pop it open over here. And that's how sulfur gets neutralized again. So the ring that remains is how big? 1, 2, 3, 4, 5, 6, 7, 8. You can draw an octagon if you want, or just draw it as you see it. That's always safer. I need to see a wedge to that sulfur because you need to show me, you know, it was a backside attack. CH2, C with 2 methyls and a P, PH3. And that's going to stay positive. It's pretty stable, actually. Are you worried about N positives in final products? Please tell me you're not. Those are stable. N positive makes weak acids, therefore it's stable, right? P positive, same story. There it is. It's nice. And that's the end of part 2. And let's see where we're at. That is also a logical spot for a break. Let you know where we're going to pick up after the break. This is like a random comment here. And that led us to talking about P being the same. And we're going to look at part 2 from the same exam. And I chose the segment. I'm not going to, there's another one on this exam that was more chapter 7 related, so I didn't choose it, although there's even parts of chapter 7 here. And we're close to the end of our course, so review is always good. Organic chemistry is a review course. So we'll pick up here, and I will see you very soon. Oh, by the way, I sent you 2 emails earlier today. I hope you've read them. Read them during the break. They might make you happy.